Good afternoon, my name is Barbara Carminati from University of Insubria in Italy. And in this talk, I'm going to provide an overview of the principal technique that we can adopt to protect the individual privacy when dealing with the data. In particular, given the purpose of the brain workshop, I'm going to focus on those techniques that we can adopt when the data are shared among multiple organizations. So in order to organize this talk, in order to organize the privacy preserving technique that I would like to introduce in this talk, first I need to present the possible way that the medical data could be shared. So the first model represents a scenario where the data, once has been collected, is released, is published, and made available to external entity that ideally can run the process, the analytics directly on this released data. According to the second data sharing model, we have that the processor can interactively ask the data directly to the data collector when needed, and the data collector will release only those data that indeed answer the submitted query. Between these two data sharing models, in this talk I'm going to focus on the data publishing. I'm not going to discuss on the interactive model just because let's say the main techniques that you can use for protecting the data release are the perturbation techniques. So the key idea is that before you release the data, you add some noise in the data such that you protect the data privacy. And one of the most used perturbation technique is indeed the differential privacy. And in this session, you're going to have a talk fully dedicated to the differential privacy. So in my talk, I will focus only on the data publishing. Here we can see two types of privacy preserving technique. The first is the data anonymization, the second is the encryption. We are going to discuss both of them. Let's start from the data anonymization. So data anonymization is the technique where basically we are going to pre-process the data before releasing this data, such that even by analyzing the published information, the released information, is not possible to identify the individual to which the published data belongs to. The most naive technique to anonymize the data is to simply remove from this published data, the data that we are going to publish, all the information that can directly link the data to the specific individual. We can call this information a personal identifying information, and this could be the name, obviously, the social security number, phone number, so all these information that can uniquely identify the individual. So the question is by removing this just personal identifying information is enough. So the answer is no. And the answer is no. We have this very famous attack that showed that data anonymization cannot be achieved by simply removing personal identifying information. Here we are basically in Massachusetts, US, where the body that is responsible for purchasing the health insurance for the state employees decide to release the medical data. So the medical information about the procedure that these employees underwent. They make this decision under the assumption that by removing the personal identifier of the employee, this data can be considered anonymous. So if you see there is in this data set, you don't see information about the name of the employees or other social security number or other personal identifying information. You see the information about the procedure that they undergone and some information about the individual, like the zip code, the birth date and sex, and the gender. So in this paper, this researcher ran in an attack where basically she linked this data set, this published data set, with another published data set, which is the voter registration list of the Cambridge, Massachusetts. And as you see in this further published data, you have information about the individual, the name, the address, and other information, plus some attributes that are common to the medical data, so the zip, the birth date, and the sex. So if you see from these two data sets, it's clear that you can link these two data sets by using the zip and the gender and the birth date. Also, the medical records of the governor, the governor of the Massachusetts at that time, were releasing the data. So the research what she done is to cross the information, and according to the Cambridge voter list, only 6 people have the birthday of the governor, only 3 of them were men, and only 1 have the same zip code. So in this attack, the researcher was able to identify the governor by, to identify the, the information in the medical data of that governor. So this example shows that it's possible to link a different data source by exploiting these 3 attributes. And by linking different data sources, you can re-identify the user. Actually, the researcher also showed that almost 90% of the population, of the US population, can be uniquely re-identified based on these 3 attributes. So how we can avoid this linking attack, this re-identification attack? The same researcher that ran for the first time this attack also proposed a privacy principle, a privacy model called key anonymity that aimed to avoid the re-identification. So the basic idea of the key anonymity is that given an anonymized data, the information about an individual should not be distinguishable from information of other k-1 individual, where k is just a parameter. So basically, you are not able to uniquely identify the record that is associated to a given individual, but you are able to identify k records among the anonymized dataset. So how can anonymity work? We need to understand which information we need to modify to ensure that for each single individual you have other k records with the same information. To understand, let's take in consideration this table where you see that you have some information that identify the user, some information that we show that could re-identify the user by the linking attack, and some information that are those information that you don't want to touch because these are the sensitive information that you need for your research. So we can classify the information as identifier, quasi-identifier, and sensitive information. As you might figure out, the identifier need to be removed. What we can modify is the quasi-identifier such to ensure that by exploiting the quasi-identifier, you are not able to re-identify as the user. Just to give an example, let's consider this table that contains the quasi-identifier and the sensitive attribute. The quasi-identifier, the zip code, age, and gender, and the disease is the sensitive attribute. And let's assume that we are going to implement a three anonymous key anonymity with key equal to 3. What does it mean? That it means that we are going to modify the quasi-identifier such that every group that have the same quasi-identifier, we have at least 3 records. And indeed, if you are an attacker, you know the Alice quasi-identifier, and you know that these are exactly these. When you look to the 3 anonymous table, you are going to find 3 records for the same, for the Alice quasi-identifier. So you are not able to understand which of these 3 records belong to Alice, but you have a confidence on 1/3. Obviously, greater is the key, better is, improve the privacy level. So how we can achieve the key anonymity? So the principle of the key anonymity is that we need to modify the quasi-identifier value such to ensure that in the anonymized data we have at least key records with the same key quasi-identifier values. So how we can modify the quasi-identifier value? One technique is to do the generalization. Generalization implies to replace the value of the quasi-identifier with a new value that is less specific, such to obtain the group of key identical quasi-identifier value. These are examples of generalization. In the case of the zip code, as you can see, in order to generalize these 3 zip codes, I need to omit 2 digits. Again, in the age, I need to omit 1 digit, or in the sex, I just simply omit all the information. Generalization implies some information loss because you are going to replace with less specific information. Information loss is obviously imply that your data is less usable, is less lose some data utility. And for example, if the age is really relevant for your research, you are not able to understand the exact age of the individual, but you are able to understand the let's say that these individuals are in the 20. Another technique that you can obtain is the suppression, so removing the data at all from the record. This is applied such to avoid too much information loss. Since the definition of key anonymity, several other privacy models has been proposed that extend the concept of key anonymity by improving the privacy level, by ensuring that no other attacks can be performed. For example, diversity that avoid inference that could be done by analyzing the distribution of the sensitive data, as well as the closeness and so on and so forth. Just to give an idea of how many privacy models has been defined, in this table I show you the tools that are available that you can use to exploit, to anonymize your data, and the privacy model that they support. So it's clear that there is no one model that fits all the situation. Indeed, it's a matter of trading off between the privacy level, so how much you want to protect your data, your anonymized data, and the data utility. So in order to understand which model you could apply in your data, you indeed have to analyze, to perform a risk assessment, analyze the identification risk, and by means of utility metrics, understand how much information you are going to lose if you apply that model or another. So I would stop the discussion about data anonymization here, and let's go to the other technique of for protecting the data in case of data publishing. So the first question that we need to answer is the encryption is enough to protect the privacy. So if I'm going to encrypt my data, this is enough to protect the privacy of my sensitive data. If you consider this example where we have the disease table with information about the possible disease that are recorded in my medical data, this record has been encrypted with the same key. So, since the encryption is deterministic, the same plaintext encrypted with the same key will generate the same ciphertext. So, what you are obtaining here is that for the two flu, the two records that have flu as a disease, these are encrypted and the encryption generates the same ciphertext. So, since the encryption is deterministic, what you can do, if I simply encrypt the data, I can infer some information about the data distribution. So, I'm not able to tell you that this is a flu, but I'm able to tell you that I have 2 items over 4 that have the same disease, which is not good in terms of privacy. To avoid to have this deterministic behavior in our encrypted data, we need to apply some standard technique. One of the most famous is this Cyberblock chaining, where basically the idea is that your message that has to be encrypted is, as you know, split in several plaintexts, and each plaintext, before entering the algorithm, know that you are going to encrypt each plaintext with the same key. So each plaintext, before and be given input on the encryption algorithm, we are going to add some noise. This is XOR operator. We are going to add some noise such that even if 2 plaintexts are equal, when they enter in the encryption algorithm, since we add 2 different noise, the input will be different on the encryption algorithm, thus the ciphertext will be different. So even the plaintexts are equal, the ciphertext will be different. According to the CBC encryption mode, basically we generate or we use as a noise the ciphertext produced by the encryption of the previous plaintext. So we can locally regenerate a noise for every step of the encryption, and this noise has to be added on the plaintext and and then the new plaintext is input on the encryption algorithm. So in this way, we are sure that if you use encryption scheme in a non-deterministic way, we are able to protect the privacy, because we cannot do any information, any, let's say, inference on the distribution of the ciphertext. But as you might figure out, you have a high privacy level, but you have a very low data utility. Indeed, on your encrypted data, you cannot perform any kind of operation. So if you want to make your published data usable, you need to have a solution where over an encrypted data you can compute some operation. And what we can adopt in this context, so in the scenario when you want that the data is private but has to be also usable, so you can have to perform some computation, are these kind of encryption scheme that are called homomorphic encryption. So how I define a homomorphic encryption scheme? So an homomorphic encryption scheme is such that the encryption algorithm is said that is homomorphic with respect to a given operator, that here is defined as a star symbol, if the encryption of a value M1 combined with the operator that we are considering the star operator with encryption of a value M2 is equal to the encryption performed over the results of M1 operator M2. So if this equation holds, we say that the encryption is homomorphic, obviously for every pair of possible message that you want to encrypt. So how it works in homomorphic encryption? So the homomorphic encryption scheme exploits the algebraic structure of the encryption algorithm. Just to give an idea how it works, given a very simple example that we can do over RSA algorithm. RSA algorithm is the first and the most famous asymmetric encryption algorithm. RSA algorithm work in this way, so this is a very simple way to see RSA algorithm, but you compute the encryption by doing modulo exponentiation. More particularly, if you consider M, the message, the plaintext that you want to encrypt, this is model that is represented as an integer, and then you have to compute M up to E is a parameter, and then you compute the module N. And then in order to decrypt your ciphertext, you need to again compute C up to another parameter D, and then compute the module N. So obviously this E, N, and D has to be properly defined according to the RSA algorithm rules. So there is some strong, let's say, math assumption in order to create E, N, and D, to generate E and D. But if you properly generate E, N, and D, these two equations works. So let's see if RSA is homomorphic. Let's consider two messages. And we have message 1 and message 2. And we want to encrypt by using the same key. So the same key means that we are using the same N and the same E, and the same N. So the encryption of message 1 is computed as M1 up to E mod N, and the encryption of message 2 is computed as M2 up to E mod N. Now let's compute this operation. So let's multiply encryption of message 1 multiply encryption message 2. So encryption message 1 times encryption message 2. So I simply replace these two values. This is the encryption of message 1 and this is the encryption of message 2. According to the property of the modulo exponentiation, what we obtain here is that it's this equation can be rewritten as n1 times n2 up to E modulo n. And this is indeed the definition of the encryption. So we can rewrite this as encryption of m1 times m2. So what we obtain is that encryption of M1 times encryption of M2 is equal to encryption of M1 times M2. So what we obtain what we show is that RS is homomorphic, but with respect of the multiplication. Indeed, if we try to do the same with the addition, we will see that it doesn't work. So we are not obtaining that encryption M1 sum plus encryption F2 is equal to encryption M1 added to M2. So RSA is really a simple example that show how it works, the homomorphic encryption, and also show that the homomorphic encryption could work only for some, let's say, some operation. For example, RSA is only homomorphic with respect to the multiplication. In this case, we say that we have a partially homomorphic encryption because your homomorphic encryption scheme, your encryption scheme, support only one operator, in this case the multiplication. So since the first privacy homomorphisms that has been introduced in the late 17, actually with the RSA, different homomorphic encryption schemes has been proposed. Actually, let's say till the 2000, all the homomorphic encryption scheme was partially homomorphic in the sense that they were able to support only one type of operation, addition or multiplication. Then we reach the somewhat homomorphic encryption, which basically is an homomorphic encryption scheme that is able to support the two types of operations, so addition and multiplication, but a limited, let's say, number of combination of the two. So the complexity of the operation that you can do is limited. Then finally we reach the fully homomorphic encryption, where basically the encryption scheme are able to support any arbitrary combination of the two types of operation. What we have to notice, however, that more complex are the operations that our encryption scheme are able to support, slower is the execution speed. As a conclusion, in this talk, I tried to give an overview about the two main techniques that you can adopt when you want to protect the data privacy in data publishing. Actually, there is plenty of different privacy model, algorithm, and homomorphic encryption scheme that you can adopt, but it has to be clear that there is no one solution that fits all the possible scenarios. Indeed, in order to find the best solution for the data management, the scenario that you have to consider, you need to do an analysis between the trade-off between the privacy and usability, and also to consider practical feasibility of your solution. With that, I conclude and I thank you for your attention.